Hey guys, this is Mr. Lowry. I wanted to give you some help on the systems of equations, applications, problems, homework. If you were in class today, we did several of these, and I'm going to kind of show you the setups for them. This is mostly for people who weren't in class today, because we did a bunch of these in class. Now, if you were in class today, and you have some of these examples, I might do one or two more that we didn't do in class. But you basically, there's a bunch of on the front, and then there's usually like a matching one on the back. Okay, so the techniques that you use on some of these, you're just going to reuse. All right, let's start with number one real quick just to get going. Now, number one is actually really similar to a problem that we had last semester, where we were talking about filling buses and vans with students to go on a field trip or something. So go ahead and, if you haven't already, pause the video, read through number one. Our goal is to really understand what's happening, and then we're going to annotate it. So go ahead and read it now. Okay, if you're coming back from pause, you've already read this. What I'm going to do is I'm going to show you how to, what we call annotate a problem. We're going to add some notes to ourselves. Okay, the first thing that we want to recognize is that we have two high schools. Okay, so we have high school A and high school B. Okay, what that means here is we have two different scenarios, which actually is going to translate to two different equations. Okay, so I'm going to go ahead and write out high school A and high school B, because I know that each one of those is probably going to have its own equations, probably going to have its own information. Okay. In fact, let me go back here. Let me box high school A. Let me circle high school B. We'll use that as some differentiation. Okay. So now we got high school A, right? We got 6 vans. We got 9 buses. We got 231 students. So I'm boxing all of those quantities that go with high school A. So high school A is in a box. All the quantities go in a box. Okay, now it talks about high school B. So 12 vans, 13 buses, 357 students. That all goes with high school B. Okay, now the last thing I'm going to read here is that I need to find the number of students in each van and in each bus. Okay, so I have quantities here. Quantities are amounts of things. I have some amounts of vans, I have amounts of students, I have amounts of buses. Okay, I also have some unknown quantities. And the unknown quantities are the amount of students in each van and in each bus. So for each unknown quantity, I want a variable. So let's do number of students in each van, we'll call X, and number of students in each bus, we'll call Y. Okay? All right, so now we can put all the pieces together. So for high school A, we have 6 vans. But we don't know how many people are in each van. Right? So we have to multiply the number of vans times X, because X is the number of students in the van. So 6 vans times some amount of students per van. Okay, we're going to add that to a number of students in the buses. So there's 9 buses, but again, we don't know how many students are in each bus. We called that Y. So if we take the number of buses and multiply it by the number of students per bus, we get a bunch of students. Okay, now altogether, the number of students that we need, is 231. Okay, high school B is going to have a very similar setup. This time they have 12 vans times the number of students in each van. They have 13 buses. We're going to multiply that by the number of students in each bus, and that should give us a total of 357 students. Okay, so notice we have two equations, and they're both in standard form, and we want to solve the system. We want to know what X and Y is. So in this case, I would probably solve this by elimination, because my X's are kind of stacked on top of each other, and so are my Y's, and then I have the numbers on the right-hand side of the equals sign. So this looks like a good candidate for elimination. I'm not going to solve it for you, but I'll help you get started. I think for me, the easiest variable to eliminate would be X, and we would get that happening if we multiplied everything in the first equation by -2, because that would give me a -12x here and a positive 12x here. So what you need to do is go ahead and distribute that -2 multiply that -2 here on the right-hand side, and then you'll add that new equation A to equation B. I feel like pretty confident that you guys know how to solve by elimination, so I'm going to let you take it from there. The hard part, I think, is setting up the equations. Okay? Let's look at a couple other examples that we're going to see, a couple different types that we can see. All right. Some of these are going to require a little bit of what we call inference. Okay? Inference means that there's some information that they're not telling us directly, and we need to kind of read between the lines here. All right, let's take a look at number 3 for a second. This is about a boat going downstream and upstream. Okay, so take a second to read the problem, and maybe even read it more than once, and then we'll talk about it. So go ahead and pause the video now and read the problem. Okay, so coming back from pause, you've just read this problem, you're trying to understand what's going on. Let's take a look at what we got here. So we have a boat going downstream and back. That means there's 2 trips, okay? And I'm going to write that down here just like I did up here. So we have a downstream trip and an upstream trip, and each one is going to have its own equation. Okay, here's some inferences that we have to make, or here's some background information that we might need to know. Okay, the first is this. When we have distance, speeds, and times, the relationship between those is that distance is equal to speed times time. Okay, or D equals ST. We're going to use that as a template to set up our equations. So this is how we're going to set them up. Another thing we need to talk about is what downstream means and what current is and how that all works. Okay, so let's talk about that. When you have a river, the water in the river is going to be traveling a certain direction. Okay, in this case, we're going to make an arrow that's going this way. Okay, so there's a direction that the river is traveling. If your boat is going with the current of the river, we say that's going downstream. We're going with the river. Okay. If we're going the opposite of the current, if we were going this way, our boat was pointed the other direction, we'd be having to go upstream, right? We'd be working against the current. Okay, so downstream is with the current, upstream is against the current. When you're going with the current, you actually can go faster because the water is pushing you and the motor of the boat is pushing you as well, or whatever is powering the boat. When you're going upstream, they actually work against each other. So when we look at what we have here, we have what is the speed of the boat in still water. Okay, so there's actually the speed of the boat. We'll call that B. Okay, when it says in still water, that's just assuming there's no current. So the boat can go a certain speed on its own. The motor or the rower or whoever is like powering the boat, it can go at a certain speed. Okay, but then there's actually the speed of the river, the current itself, that could be pushing the boat. Okay, so let's say your boat's max speed is 20 miles an hour, but you're going 20 miles an hour with the current and the water is moving 5 miles an hour. Well, the speed of the boat in still water would be 20, but you're actually moving with the current at 5 miles an hour, so together you're going 25 miles an hour. So this thing where it says in still water is just to differentiate what's the boat by itself without the current, and then what is just the current. Okay, so speed of the boat we'll call B, and then speed of the current we'll call C. Okay, so now let's set up the equation. Okay, the boat traveled 312 miles downstream and back. So the distance for both trips is the same, 312 and 312. Okay, it's the same distance. So this is the D, right? I'm writing D equals. So D equals ST. I'm using this DST as a template for setting up my equations because I have this relationship for both trips. So 312 miles is the distance, okay? The speed we're going to come back to in a second, so we'll ignore that for now. And then the time is the other variable. So the first trip, the downstream trip, is 13 hours. So there's a 13 here. And then the upstream trip, when we went back, that was 39 hours. Okay? Now here's where it gets a little tricky. Okay? The speed, when we talk about speed, remember that there's 2 components of speed. There's two pieces. There's the boat speed and there's the current speed. Okay, and it depends on whether we're going with the current or against the current. Will make a difference here. So when we're going downstream, the speed of the boat and the speed of the current work together. So for speed, instead of speed, we actually have two speeds. We have the boat speed and the current speed, and we're going to add them together to get our total speed. So this is equation 1 now, all set up. Okay. For upstream, we're going to be going against the current. We're going to be fighting the current going up. And so we have to actually subtract the speed of the current because we're going to be working against the current as we push against it. Okay. So distance is the same for both. The time for the first one is 13 hours. The time for the second one is 39 hours. That's because we're going faster downstream, so it takes less time. We're going slower upstream, so it takes a lot more time. Okay? Then there's the two parts of the speed, the boat speed added to the current speed for downstream, and the boat speed subtract the current speed for upstream. So here's a system. Okay? We just need to solve it. Now there's a couple ways to go about this. And there's not necessarily a right or wrong, but there's maybe an easy and a less easy. So I could take this 13 and distribute, and I could take this 39 and distribute. Okay, but actually, it's a lot easier to just divide it out from both sides because this is b plus c times 13 and b minus c times 39. So we can just divide both sides. Okay, so check it out. I'm going to do both of them here. So 312 equals b plus c times 13. What I'm going to do is I'm going to divide the right by 13, and I'm going to divide the left by 13. Okay, this is for equation 1. Now again, you could distribute and do it that way, but I think this is a lot easier. Okay, if you do 312 divided by 13, that actually comes out to be 24. And then here the 13s cancel. So 24 equals b plus c. All right, that's just a different version of equation 1. That's the downstream equation. Okay, for the upstream equation, I'm going to do the same kind of idea. So, this was b minus c times 39. Okay, I'm going to divide both sides by 39. And so if you do 312 divided by 39, you get 8. So 8 equals b minus c. So now here's my two equations. 24 equals b plus c, 8 equals b minus c. I'm going to write them over here. Okay, now you can do elimination here pretty easily because the c's are going to cancel. It's all set up for you. Okay, so let me, get you going one more step here and then I'll let you finish. So this is 32 equals b plus b is 2b, c and negative c cancel, so I get 32 equals 2b. If I divide both sides by 2, I get 16 equals b. So that's how fast the boat can go by itself, not including the current. Now what we need to do is we need to find the speed of the current. This is the speed the boat can go. So we can take this 16 and we can plug it in either here or here. We could also plug it in here or here. Doesn't matter. We have 4 different equations to choose from, but one of these is probably going to be the easier one to deal with. Okay, so I might put it in here. So plug the b in and then solve for c. That will give you the boat speed and the current speed, excuse me. All right, now what we kind of want to do maybe at this point is we need to start trying to match up some problems here, find some patterns, okay? So if you look at number 3, it's this boat downstream upstream problem. So I call this a downstream upstream problem, and we can kind of label it that way. We have several problems that we're going to do, and so we might want to look at the back and see if we can find a problem that's similar. Okay, if you look a little bit, there's not really one that has to do with boats, but there is one that has to do with traveling, and that's number 13. So let's take a look, and let's see if we can set it up again. A plane traveled 560 miles to Las Vegas and back, right? So 2 trips. There and back. Okay, there's 2 of those. Remember, we're using d equals st, distance equals speed times time for each one. the distance is the same for the trip as it is back, right? If I fly to Las Vegas and it's 560 miles, when I fly back, it's got to be the same 560 miles back. So there's the D, the distance for both of them. Okay, equals. Okay, now this one doesn't have current, obviously, because we're not talking about water anymore. We're talking about wind. Okay, we have into the wind and we have with the wind. Same kind of idea. So if we have like a little plane here, let's see if I can draw a plane. It's a pretty bad plane, right? But the wind's blowing. If the plane's blowing with the wind, it's pushing the plane and making it go faster. When the plane comes back, it's flying into the wind and the wind's pushing against it and it's making it go slower. So we have the speed of the plane by itself. So it's called the still air speed, right? Still air because it's like how fast can the plane go without thinking about the wind at all, right? We'll call that P. And then there's the speed of the wind, which we'll call W. So instead of, the boat and the current, we have the plane and the wind. Same idea. Okay, so the next part is the speed, right? But remember, there's two components to speed. So distance equals, here's the speed part. The speed part goes here. When you're going with the wind, the speed of the plane and the speed of the wind work together to give you your total speed. So plane plus wind. And that is going to take you 7 hours. Okay, that's the first trip. Okay, on the way back, it takes a lot longer. It takes twice as long because you're flying into the wind. So your speed that you're multiplied by your time here is the plane speed minus the wind speed because they're going to be working against each other. Okay, so sorry, this W is kind of in the way. We just wanted to label the wind speed W. But the setup of our equation here, here's distance. Okay, here's speed, right? Speed and speed. Now there's two components to speed that we need to take into account. And then the last piece is the time. Okay, so distance, speed, and time. Distance equals speed times time. Distance equals speed times time. Okay, that's the setup. All right, now, again, the speed of the wind we call W, and then the speed of the plane we call P. We need to find each of those. So what I would do here is I would get rid of the 7, divide both sides by 7 on top. That will give you just P plus W. Divide both sides by 14 for the bottom one. Divide that 14 out. That will give you a P minus W equation. And then you can put those together, combine, do your elimination, and you'll find the speed of the plane and the speed of the wind. Okay? That's probably the hardest kind there are, so I wanted to make sure I helped you set up both of those. But that's tricky there. Okay, let's take a look at number 4. We're just going to keep on going here. I'm going to give you lots of examples to work with. And again, we did a lot of these in class. Okay, so on number 4, we have sum of two numbers and difference of two numbers. That's actually going to give us our two equations here. So we have a sum equation and we have a difference equation. Okay, there's two numbers and I don't know what they are. They're unknown, right? The sum of two numbers is two numbers added together. So sum means add, right? Is means equals. I don't know what the two numbers are, but I know what their sum is. So some number plus another number equals 21. Now since I don't know what those numbers are, they're unknowns, why not just call them x and y? Okay, you don't have to use x and y on all these problems. You can, though. The variables that you pick are up to you. You can use, a's and b's or whatever. Usually x and y's is our default. So there's our sum equation. Okay, their difference is, so two numbers, difference means subtract. So I'll put a subtract under difference. Is equals. So I have a subtraction of two things. I don't know what those two things are, but I know what the difference is. I know what the end result is. The end result is 5. But those numbers that we're talking about are the same two numbers. Okay? So notice that this is actually set up for elimination. This looks really, really convenient here that the y's are going to cancel. So if I add these two together, x and x is 2x, y and negative y cancels, and then 21 plus 5 is 26. Okay? Now, that's not the end of the problem. We still got to find x, and then we got to find y, but that's at least going to get you a lot of the way there. So divide both sides by 2, you'll find out what x is. Take that x and plug it back into one of the two equations, and you can figure out what y is. Okay, so there's two equations, one for the sum and one for the difference. Okay, you got your numbers you don't know. There's two numbers that you don't know. We're going to call them x and y. And then we set up our equations. Okay, let's look for the one that's similar to that on the back. Okay, so 4 is going to look a lot like, oh, maybe I didn't put another one on like that on here. Yeah, it looks like I might have gotten rid of it. That's okay. That's good to know. That's a good like ACT question you might see. Okay, let's keep going here. All right, here's another problem you're going to see. This one actually for sure is on both sides. Okay, and this one has to do with rectangles. So go ahead and read this, pause it if you need to, and try to like organize all the information yourself. Okay, coming back from pause, this one's a little tricky here. Sometimes the best thing to do when you have a scenario is to draw a picture, if that helps. Okay, so in this case, we're working on a picture frame. And so we have 4 sides of the picture frame, right? This is all inference. This is stuff that they're not telling you directly. It's stuff that you kind of have to read between the lines. Okay, so we have our picture frame that has 4 sides. And we have width and we have height. It's talking about width and height. So this would be width and this would be height, right? But if this is width, then this over here has to be the same number, right? Whatever W is, it's also W up here. And this has to be H here. Okay, so I have 72 inches of wood to use. So this plus this plus this plus this, all 4 sides added all up together, better equal 72. So one of my equations has to do with the amount of wood we're using. So here's your wood equation. H plus W plus H plus W equals 72. Well, we can actually combine like terms there. So there's 2 H's, right? H and H. And there's 2 W's. And that all has to add together to get 72. Okay? This idea of measuring around a rectangle is called perimeter. So this right here, 2H plus 2W, is called the perimeter of the rectangle. The perimeter, or like the edge, right, around the outside of this frame, has to be 72 inches. You don't have to know that word to be able to set up and solve the equation, but just so you know, that right there is the formula for perimeter for any rectangle. 2 times the height plus 2 times the width. Okay? So that's equation 1 right here. It comes from that 72 inches along with kind of the picture and that inference that we made. Okay, the next equation comes from the relationship between width and height. So check it out. The width of her frame needs to be, so needs to be would be equals, and then 4/5 of the height of is a multiply. So let's translate that sentence. This sentence is actually going to be equation 2. Okay, so this is the relationship between the height and the width. So width needs to be, or is, has to equal, width equals 4/5 of times height. Width equals 4/5 times height. Okay, that's the second question, the second equation, excuse me. So if you think about like what should we do here, right? Well, we got to take, I mean, there's more than one way to do this, but if it was me, I would look at this and say, okay, W's by itself, W equals, right? That means replace W. This is going to be a substitution problem, okay? We're going to replace W with what it's equal to, and we're going to do that right here. We're going to replace that W in the other equation. So this equation tells us we can replace W with 4/5 H, and we can do it right there. So we're going to rewrite equation 1, the wood equation, and we're going to replace W. So we got 2H plus 2 times W, but instead of W, I'm going to do 4/5 H, and that's equals 72. Okay, now I have an equation that only has H's in it. When we simplify here, 2H plus So if we have this is a 2 times a 4/5 times an h. So if we want to write that 2 as a 2 over 1, we can. 2 times 4 is 8. 1 times 5 is 5. Okay. This is the equation we now need to solve for h. 2h plus 8/5 h equals 72. There's a couple ways to do this. There's you can get common denominators with the h's if you want to, because you need to combine these. They both have h's in them. But what I would do here is a technique that we've talked about before called clearing the fraction. Okay, so what we do is we find the lowest common denominator, right? Well, there's a 5. This one just has like a 1, and this has a 1. So the lowest common denominator of all of these guys is just 5. So what we're going to do is we're going to multiply everything by that lowest common denominator. I'll show you what's going to happen. First, we have to distribute the 5. So I have 5 times 2h, and then I have 5 times 8 over 5h. So this 5 times this piece as well. I got to distribute first. And then I have 72 times 5. So notice every piece is getting multiplied by 5. Okay, here's a 10h. Now what happens here, and again this is a strategy we've used before, the 5 up here and the 5 down here cancel, which is why we multiply by 5 in the first place, and we get an 8h. Okay, 72 times 5 happens to be 360. And so now I have 10h plus 8h equals 360, or 18h equals 360. Okay, so you can go from here. You can divide both sides by 18 and find out what h is. Okay, from there, you're going to plug that back in, probably to this equation. It doesn't really matter which one. You could use either. You could use this one or this one, and you're going to find out what w is. Okay, we've already talked about substitution before. The differences here is, of course, first you have to write your equations, which is hard, so I wanted to help you with that. The other thing is this fraction idea. Now, we've dealt with fractions before, and again, this strategy that we've done before is called clearing the fraction. It's not the only way to solve an equation that has fractions in it, but it's kind of a nice way because you get rid of the fractions. What you do is you multiply everything by the lowest common denominator, and it gets rid of all the denominators. Okay, so I'm going to leave that one with you there, but let's go ahead and check out, what that kind of like looks like, or what that one goes with on the back side. So that was about a wooden rectangle, wooden frame. If you take a look at these here and you try to find one that kind of has to do with rectangles, you'll see that this one has to do with rectangles. Okay, so you have a rectangular plot of land for a garden, you have some feet of fencing to use, you have a relationship between length and width, okay, and you need to solve it. So use this as an example on what to do, right? Well, if you have a fence that's going around a plot, you're going to have this perimeter idea still. It's just not going to be equal to 72. You're also going to have a relationship between width and height. It's just not going to be 4/5. It's going to be a different relationship. So set up your equations like this, probably going to use a substitution, and then you can go from there. Okay? A couple more here. Again, this is mostly for people who missed class today, but if you were here, this will help you as well if you need it. Okay, the other type of problem that you're going to see here is what's called a break-even. Okay, so number 6 is a good example of a break-even problem, right? See break-even. And what you want to know about break-even is break-even happens when cost equals revenue. The money you're spending is the same as the money that you're earning. So revenue is the money coming in, right? The money that you get, the money that you collect. Cost is the money going out, the money that you're spending. So breaking even happens when you've basically recovered all of your costs. Everything that you've spent, you've made back. Okay? So in a question like this, you actually want two different equations, one for cost and one for revenue or income. In this case, we got Ralph, and he's selling bikes, and we have two kinds of costs. We have this cost, this money he's paying for rent and utilities for his bike shop, that he only has to pay once a month. It doesn't matter how many bikes he makes, he has to pay that. But he also has this cost. He has to pay for the parts for the bikes that he builds. He has to buy those from some supplier. So Ralph's cost equation has two pieces. It has the $50 per bike. That's the variable cost. So let's say 50 times B. And then he has the fixed cost. The fixed cost is the one that he has to pay no matter what. It doesn't depend on bikes. The variable cost depends on how many bikes he makes, right? There's a B in it. The fixed cost doesn't depend on how many bikes he makes. It's just a one-time thing. So depending on how many bikes he makes, he'll have to pay more. His cost will be more. Okay, revenue or income, if you want to call it that, the money coming in, there's only one piece to it. He's selling his bikes for $175. So his revenue depends completely on how many bikes he sells. In this case, he'll sell each bike for $175. Okay, now here's the key. We want to break even. Okay, so we want cost to equal revenue. Now typically we use different variables for cost and revenue, but break even tells us that cost equals revenue. So if cost equals revenue, then I can replace this with 50B plus 2750, and I can replace this with 175B. Right? B stands for how many bikes he needs to sell. So if we solve this equation for B, group all the B's together, and then, get B by itself, we can figure out how many bikes he needs to sell. So B equals bikes sold. We're going to assume that the number of bikes he makes is also the number of bikes he sells. We're going to assume he's going to be able to sell. If he makes a bike, he's going to sell it. Okay, so that is the equation. Now, it's not done here. You're going to have to finish this. You need to solve for B. But that's the setup with a break-even problem. You need a cost equation with your variable and your fixed, and then you need a revenue equation with the amount you're selling them for with your variable. Okay? Again, if we take a look at the back, we'll notice that we got another break-even here on number 11. Okay? So if you're not sure how to set up number 11, that's, pretty normal, but you have an example back there on number 6 that you can set up. Okay, so we got similar examples on the back that we have on the front. Okay, let me do one more with you that is kind of a little bit tricky. All right, and I'm going to look at number 7. Okay, number 7, it's kind of hard to find the other equation, and I'll show you what I mean by that. Okay, so in this case, we have Raul purchasing school supplies. He needs notebooks and binders. Each notebook is $250, each binder is $325, and Raul has $18 to spend. Okay, so one of the equations that we're going to write is for total amount of money that we're going to spend. Okay, we have notebooks and binders. Let's do notebooks as X and binders as Y. You could use N and B if you wanted to. It doesn't really matter. But this is the total money equation, right? Each notebook is $2.50, so I have $2.50 times X because I don't know how many I'm going to buy. And then I have $3.25 times Y, and I don't know how many I'm going to buy of binders. But I do know that I want to spend $18 total. Okay, so I have $250 per binder times the number of, $250 per notebook times the number of notebooks, $325 per binder times the number of binders equals the total amount of money. Okay, so when you look at that and you're like, okay, cool, like I got the $250, I got the $325, I got the $18, you're like, what's the other equation, right? Well, this is where it happens right here. He needs a combination of 6 notebooks and binders. So you got 6. So the other thing is we have total amount, okay, and the total amount needs to equal 6. Let's say you have 6 classes and you need either a notebook or a binder for each one, right? So 6 total products. But what is the rest of it? What are the other numbers? Well, if you remember, X was the number of notebooks and binders was the number of Y. X was the number of notebooks and Y was the number of binders. So the other equation is x plus y equals 6. Kind of tricky, right? Here I have the number of notebooks multiplying their cost and the number of binders multiplying their cost to get a total cost. The other equation is actually a total amount equation. X represented the amount of notebooks and Y represented the amount of binders, and I need 6 of them total. And so this is the second equation. They're not both the same kind. There's not cost and cost or money and money. It's actually, there's a money equation and there's an amount equation. Okay, so we can solve with substitution or with elimination from here. It's up to you. I probably would do elimination, and I would do something like multiply the bottom by maybe negative 2.50, multiply everything by negative 2.5 so that the x's will eliminate. Okay, if you do that, the bottom equation will become negative 2.50x minus 2.50y equals, that's going to be a negative, let's see, 6 times 2.5, 15. So that'll be a negative 15. So put that equation with that equation, do your elimination, the x's are going to cancel, and you'll be able to solve for y. Plug that back in, you'll be able to solve for x. Okay, so that's a little bit tricky. Now that one actually goes with 12 here. Okay, this 12 here with Darius. So we have cost for sandwiches, cost for salads, total amount of money, but then also he needs a total amount of lunches. Okay, so your first equation is going to have like a 650x and a 775y equals 105. But your second equation is going to be basically like x plus y equals 15. So very similar to where it's like, okay, well, here's the money equation, but there's another that just has the amounts of how much you need. 6 total products, right? Again, same thing down here. You got some stuff with money, but you also have a total amount of lunches that you need. So the x and the y have to add to 15. So that's another one there. Okay, I think the rest of these, you have either an example from the previous side or you can kind of set them up. I think you can handle some of these on your own. So, you have your rectangle problem here, number 9. You have a kind of a total cost and total amount problem in number 12. You got your kind of upstream, downstream problem in number 13, only it's upwind, downwind. It has to do with wind instead of current. And you have, in number 11, you have another break-even problem. Okay, so that should get you started, help you set these up. I know it's kind of hard to set these up, but once you have them set up, you know how to solve these with either substitution or elimination, and now you have a lot of good examples to help you get going. Okay, I hope that helps. Do your best. Don't leave anything blank. Show all your work, and you'll get full credit on this one. Thanks.